Well, we have an exam, a lovely exam. Differential equations. This is exam 2, so we're talking about systems of differential equations. In other words, matrices. Good stuff, good stuff. Fall 2024, excellent vintage. We've got 6 problems that we're going to work through. And of course, as always, we're going to start by putting our name. Because if we don't put our name, we won't get the credit. All right, let's go. Our first problem, lots of words, but let's see what we have. There are 2 large tanks. Yep, those look pretty big. With brine solution, and brine is just another fancy way of saying salty water. And they're set up as illustrated in the following diagram. So, what happens? Into the tank 1, we have some inflow, 9 gallons per minute. There's 3 ounces per gallon. And then we have some outflow to tank 2 and some inflow from tank 2. And then in tank 2, well, we again have the inflow and the outflow, and then outflow out of the system. Now, notice a couple things. 9 gallons coming into the system, 9 gallons going out. Good. And if you look at each individual tank, you get 9 plus 9 in, 18 out, which means net 0. In this tank, 9 and 9 out, 18 in, net 0. So that means nothing's going up in terms of water level, nothing's going down. Whew, good, that makes things simpler. Moreover, we have that initially at t equals 0, tank 1 has 125 gallons of brine and 14 ounces of salt. Okay, so tank 1, this has 125 gallons. Now, we just mentioned the water levels are not changing, so that's always 125 gallons. The 14 ounces, that might change. Okay, so we'll make some notes here. Let's suppose we call, do we have any names? Let's say X1. This is salt in tank 1. Then we can say initially x1 of 0 equals 14. Tank 2 has 135 gallons, and 16 ounces of salt. Now remember, again, we're talking initially. It's always going to be 135 gallons because we're not changing the level of water. And but the salt might change. So we say, okay, same deal. x2 equals salt in tank 2, x2 of 0 equals 16. Okay. And note that flows are such that the volume of solutions each tank is constant. Well, we already talked about that. Set up, but do not solve. These are some of the best words to see in any math class. But do not solve. So that means that we only have to set it up. An initial value problem of the form x prime equals a of t x plus f with initial conditions x of 0 that models the amount of salt in the 2 tanks. All right, well, let's think about what's going on. So we say we know what x1 and x2 are, so we can start by saying, well, what's going on with the change in x1, which is another way for saying x1 prime. How is the salt changing? Well, what can we see? There's salt that comes in. Now, if we look at this, we see we have 9 gallons per minute, 3 ounces per gallon, and so if we combine those two, we would have an inflow of plus 27. And that's just always 27. 27 ounces are coming in every minute. Okay, so that's that flow. Now we say, well, look, we also have something else that's coming in. We have something coming in from tank 2. Now, what do we have? We have 9 gallons of the 135 gallons from tank 2 are coming in. We can think of that as a ratio. So, in other words, I'm going to write plus because something's being added, 9 over 135. And so this is the proportion of what's in tank 2 coming into tank 1. So if that much of the water, the seawater, salty water is coming in, then that's the proportion of the salt from tank 2 going into tank 1. So plus 9 over 35, 9 over 135 times x2. Subtract, because we have this outflow, so we're losing salt. How much? Well, we're losing 18 gallons, so it's 18 over 125. That's the proportion of salt leaving times x1. Okay, so that's accounted for all the pieces attached to tank 1. So there's our setup for x1 prime, how x1 prime is changing. Now, let's do same thing, but we'll do it for x2. So x2 prime. Well, here we have this piece, and now that is an outflow. And so we don't have the same situation over here. See, here we knew how salty the water was coming in. Here we don't know. And in fact, what we can do is we can say, look, this is an outflow, this is an outflow, and outflow is an outflow. And so how much is going out? Well, 18 gallons per minute. And so that's the proportion of that would be, we're going to be losing, so I'll put a minus here, 18 over 135 x2. That is putting both of these together. We also have inflow. How much is coming in? Well, we have inflow from tank 1. How much of tank 1 are we getting? Well, 18 over 125 of tank 1. So plus an increase, 18 over 125. All right, now, this is the system. It's just not written in that form. And the other thing, of course, we haven't written down is the initial conditions. So we should write those down as x1 of 0 is 14. And x2 of 0 is 16. Okay, so we're basically done except for just writing it in the right way. Okay, so what's the right way to write it? Well, here we go. One way we can do it is we'll do it x1 prime, and now we'll put things in order. The variables in the right order, so we have minus 18 over 125 x1 plus 9 over 135 x2 and plus 27. All right, good. And x2 prime, well, what can we do here? Well, same thing, right? So put the variables in the right order. 18 over 125 x1 minus 18 over 135 x2. Now, there's no plus 27. We can think of it as a plus 0 if you like. And then we have x1 of 0 equals 14, x2 of 0 equals 16. Now, a comment. You might say, hey, does 9 divide into 135? And the answer is yes. It's 1 over 15. And, okay, should we change that, update it? Yeah, we probably should. Would we lose points? I hope not. They didn't say simplify as much as possible. And so we'll make a quick little comment. So 135 is divisible by 9. And as I said, it's 1 over 15. And this term here is 2 over 15. 18 and 125 share no common factors. 125 is 5 times 5 times 5. And all right, so now we basically can read off our system. So this part is the x prime. This part is your ax. And here's your f. So what we have is we have x1, x2 prime is equal to, and now put in the coefficients, minus 18 over 125, 1 over 15, 18 over 125, and minus 2 over 15 times x1, x2, plus this vector, 27, 0, and with x1, 0, x2, 0 equals 14, 16. All right. So there we go. There's our answer. What a lovely answer. What a lovely answer. All right. Well, that was the setup. And that's all we needed to do, was to set it up. All right. So now we keep going. Number 2. Consider the second order differential equation, x double prime minus t squared x prime minus 2tx equals cosine t. Transform it into an equivalent first order system of differential equations of the form, and then we have the derivative of x. Now notice there's a little arrow on top of that. That little arrow means it's a vector. And so sometimes we use like a bold x, sometimes we use x with a vector. There's different notations, but they all mean the same thing. A of t, and again that vector x plus this vector function f. What are the vectors of unknown functions x, the matrix of coefficients a, and the vector of functions f in the above system? Okay, so what's going on? Well, essentially there's sort of a trade-off, which is we say the number of things that we're solving for and how many derivatives we're willing to take. So right now we're saying, look, we're solving for one thing, but we're willing to take 2 derivatives. But we can switch and say, look, we'll solve for 2 things, but only take 1 derivative of each of them. And so there's this balancing act. Now, what's the right way to do it? Well, it's not that there's a right or wrong. It just depends on the techniques you have available and what tools are best to work with. In many respects, it turns out we like systems, and in part because computers are really well designed for matrices. So we say, okay, let's do our balancing. So what we're going to do is we're going to introduce some new variables. So we're going to let x1 be the actual function that we're interested in, x. And now we're going to let x2 equal x1 prime. In other words, that's x prime. And we stop here. We don't need to go any further. Because I claim now we can rewrite this differential equation, right? Because what do we have? We have x double prime minus t squared x prime minus 2tx equals cosine of t. Now, parts of it are easy to copy, right? Anything without an x, that's just going to copy straight down. So we have minus 2t minus t squared. Now it's just, what do we do with these pieces? So the x becomes our x1. Our x prime becomes our x2. What about x double prime? We didn't introduce a variable for that. Well, notice x2 is x prime. So if I take another derivative, that would give us x2 prime is x double prime. Or another way to write this is, hey, x2 prime is equal to, we're going to move stuff across, and I'll go in order of the subscripts here. So 2tx1 plus t squared x2 plus cosine t. Now, that's not the only equation we need to pay attention to. There's 2 equations we need to pay attention to. But don't worry, we're almost done. And you're feeling like, wait, what do you mean we're almost done? We've barely started. Well, notice we have these 2 equations. So one of them coming from sort of building up what I like to think of as the ladder of our equations, and then one coming from the original equation. Okay, so if you're ever doing this and you have a long equation, what you'll end up with, whatever your order is, that's how many equations you'll have. And if it's, say, a third order, you'll have a couple equations from here and then one equation from translating. And so you always have like one like really oddball one and then the rest. All right, so let's put these together. So what do we have? We have x1 prime equal to, going to leave a gap, not too suspicious, but it'll be clear once you write down the other one, x2, and x2 prime is equal to 2tx1 plus t squared x2 plus cosine t. And at this point, what's going to happen is we have essentially our pieces. So this is our x right here. This part right here is our a times x, and this part is our f. So we now write it in that form. So we have our x1, x2 prime is equal to, read off your coefficients. Now there's no x1 here, so that's a coefficient of 0, 1. Here, 2t, t squared. And make sure your coefficients go in the right place. It's not 1, right? The coefficient of x1 is 0. So make sure your coefficients are in the right place. All right, x1, x2, and then here, this is 0 because there's, if there's something missing, it's a plus 0, right? We could even fill in 0 x1 plus, and cosine t. All right, now I'm going to box it, and we'll just make some notes here. This is our a of t. This is our f. And we'll go ahead and throw a little vector on top because they seem to like little vectors. And there we go. There we go. Isn't that great? Yes. All right. Well, let's keep moving right along. All right. Now, on this problem, we're doing the opposite of what we were doing in the previous problem. So in the previous problem, we had a single equation, and we turned it into a system. Now, we have a system. What are we going to do? We're going to transform this system into a single differential equation in terms of x. All right, so in other words, instead of x and y, we're only going to have x. All right, so good news. Again, do not solve the equation. Whew, good, good. We're really good at not solving equations. All right, so what do we do? Well, I like to use Cramer's rule. And Cramer's rule is essentially about elimination. What's happening here is we are trying to eliminate the y's. We want the y's out. We only want x's. And Cramer's rule gives us a way to systematically carry out elimination. And so to get to Cramer's rule, we first have to write this in some sort of a matrix form. So that's our goal. We're going to get right into matrix form. So we begin by removing all the x's and y's across. All right, well, let's do that. What do we have? Well, so we're going to move here. We subtract x, so x prime minus x, subtract the y, minus y equals minus e to the t. Now here, we're going to add the x, and then we have the y prime already, and we'll add the y, so plus y, and that equals e to the t. Okay, so we're moving all the x's and y's to one side. Things without x's and y's are on the other side. Well, with this in place, we're now going to rewrite anything with derivatives using our notation with d. So d is for derivative. It's like the song, right? D is for derivative, that's what it means to me. D is for derivative, that's what it means to me. Yeah, D is... Oh, sorry. We could be singing that all day. But we got to focus. We got to finish this test. All right, so what happens? Well, x prime will become d times x, but we also have a minus x. So this becomes d minus 1x, and then minus y. Then we have the x, and similarly, y prime is d times y plus y. It means that we have a d plus 1y. Whoops, I don't know why I put a parentheses there. Sorry about that. Sometimes I get so excited about parentheses. Okay, now, from here, we say, look, it's almost there. We almost have our matrix. We just gather our coefficients, and lo and behold, there we have our beautiful matrix equation. All right, well, great. Now we're ready. we're ready. We're going to focus on Cramer's rule. Remember, what are we after? We want to get just x. So we're trying to solve for the x part. We're trying to get rid of the y. So to get there, we say, okay, what do we do? Well, we're going to take some determinants. So we're going to take the determinant of this matrix. So we have our d minus 1, 1, d plus 1 times x, because we're trying to solve for x, is equal to another determinant. Now, here is where we need to pay attention. There's x and y, and we have to pay attention. What is the x column? What is the y column? Well, the x column is the first column. See how x is the first entry? First column. The y column is the second column. Second entry, second column. So what we're going to do now is we're going to take this determinant, but we're going to modify it by replacing the x column. So that's the first column. And then we leave the second column alone. Okay. Well, let's go ahead and do this. D minus 1, d plus 1, right, determinant. Subtract 1 minus minus 1, subtract negative 1. Okay, so we're going to times that by x is equal to, now here, determinant, so we're going to have d plus 1 times minus e to the t, and then we're going to subtract e to the t. Okay. Well, here we'd have d squared plus d minus d and minus 1 and plus 1. And like, wow, that's a lot of canceling. So we have d squared times x, which is x double prime, right? Two derivatives. Over here, all right, we take the derivative of e to the t. That's minus e to the t. Then we're going to times 1 times minus e to the t, so that's minus e to the t. And then, oh, wait a second. I did this wrong. But I can fix myself, right? I notice how I did minus e to t, but it should be minus e to the t. So I forgot to put that in. Minus e to the t. So it's really a plus e to the t. Check yourself. As the great philosophers of mathematics would say, you should check yourself before you wreck yourself. Those cancel. So our final equation, x double prime, is minus e to the t. Wow, that's pretty clean. That's nice. That's great. We love answers which are very clean. All right, well, good. Let's keep moving along. Number 4. Solve the following system using the matrix exponential. Okay, so we have dx dt is 0 minus 3, 3, 6x, and x of 0 is minus 2, 1. So we know what we're going to need. We're going to need to use the matrix exponential. So if we solve in some other method, we're not going to get all the points. And we want to get them all. Okay, so with that in mind, we start thinking, okay, what do we need to know? Well, the first thing we need to know is, for this matrix, what are the eigenvalues? Okay, so step 1, whenever you're faced with a matrix and you're trying to solve it, you find eigenvalues. Okay, so we're going to take our a minus lambda I. So this is our a. And so that's going to become, take the determinant of that. So that's the determinant of 0 minus lambda, and then minus 3, and then 3, and 6 minus lambda. Okay, so becomes what? Well, minus lambda times 6 minus lambda, subtract 3 times negative 3. Well, that's negative 9. And if we multiply this through, minus lambda times minus lambda, that's lambda squared. Then minus 6 lambda and plus 9. Now, we have to believe that our teachers love us, because they do. They want us to succeed. Actually, they want us to get the right answers because it makes it easier to grade. So I encourage you, be nice to your teacher. Get the right answer. And okay, so what are we going to do? Well, this should factor. Do you see how? It factors as lambda minus 3 squared. Now, what are we doing? Well, ultimately, to find the eigenvalues, you set this equal to 0. And so this says, our eigenvalues are going to be 3 and 3. In other words, we are repeat eigenvalues. Okay, well, that's important. That's going to affect how we go about solving it. Now, there's a couple ways to solve this using the matrix exponential, but we want to be efficient. And we know that when we have repeated eigenvalues, that there's a very nice formula. And so here, let's write down our formula. All right, so we'll write it right here. E to the AT is equal to e to the lambda t times the identity matrix plus t a minus lambda I. Now, this is a very special case. To be clear, this only applies when you have a 2 by 2, but good news, that's what we're working with, and repeated eigenvalues. And if you don't have those two things, this formula doesn't apply. But we do have those two things. And so we say, oh, well, then the formula applies. So in our case, we say, well, lambda is 3. So we have e to the 3t times the identity matrix 1, 0, 0, 1 plus t times a minus lambda I. And if you look, how can you find a minus lambda I? Well, you have a minus lambda I written here. You just put in lambda equals 3. So we have minus 3, 3, 3, 3. All right. Or if you like, this is e to the 3t times 1 minus 3t, minus 3t, 3t, 1 plus 3t. All right. Good. Now, how do we use that to solve? So we have the matrix exponential, but the problem wasn't find the matrix exponential. The problem was solve using the matrix exponential. And so now it's our fun little thing to remember that says, oh, if you have the matrix exponential, and in general, we should say if you have x prime equals ax and initial conditions x of 0, then the solution is x equals e to the at x0. So the point is we have e to the at, we have x0, so the last thing for us to do is multiply, and then life is good. Life is wonderful. So our answer, x, will be e to the 3t, 1 minus 3t, minus 3t, 3t, 1 plus 3t, times minus 2, 1. Okay, that's e to the 3t, and then we have minus 2 times 1 minus 3t, so that would be minus 2 plus 6t, okay, and then minus 3t, and then we get minus 2 times 3t, which is minus 6t, and then plus 1 plus 3t, which becomes e to the 3t, and then we have minus 2, and 6t minus 3t plus 3t, and then we have 1, and then 3t minus 6t is minus 3t. And that's it. There's our answer. Oh, this was great. So, remember, when you're faced with a system, find your eigenvalues. Now, there's a couple of cases, right? Repeated, complex, distinct. Repeated is kind of our favorite, because if it's repeated, it's quick to find e to the at, and now The solution is e to the at times initial conditions. Plug it in. Complex, actually not too bad. There's a formula for it on the formula sheet. Same process. Distinct, that's a little bit of work. But that's not this problem. All right, number 5. Consider the following first-order linear system with constant coefficients. Okay, we have x prime equals 3x minus y, and y prime equals 5x minus 3y. And it says, okay, verify that x1 equals e to the 2t, e to the 2t, and then x2, e to the minus 2t, 5 e to the minus 2t, are solutions to this system. All right. Well, okay. And then there's a part B, but let's do part A first. Well, looking at part A, I'm tempted to rewrite this system. So I'm going to go ahead and do that. So this system says I have the derivatives on this side, so I'm going to use x to stand in for the vector, where it's x, the vector value function, where it's xy, is equal to, and then we have our 3 minus 1, 5 minus 3, x. All right, so that's just another way to write it in vector form. And so now, with that way, it's a little bit cleaner to go through and verify things. And the nice thing about verify is that we know the answer. We just have to do the work. And so verify should be free points. And so we're like, thank you. Thank you for giving us free points. But we still have to do the work. Okay, so here we go. Let's do our x1. All right, so we'll start by saying, what is x1 prime? X1 prime, well, take the derivative. And the way we take derivatives of vectors is term by term. So that would be 2 e to the 2t, 2 e to the 2t. All right. Now, on the other hand, we say, well, look, if I take our 3 minus 1, 5 minus 3 times our x1, well, that's 3 minus 1, 5 minus 3 times e to the 2t, e to the 2t, which becomes 3 e to the 2t minus e to the 2t, and then 5 e to the 2t, subtract 3 e to the 2t, which is 2e to the 2t and 2e to the 2t. And here's the important thing to say. That these two things match. Matching means it's verified. So in other words, you plug this into both sides, you get the same answer. That verifies the equality. So, good. That's x1. Now, do the same thing with x2. Okay, so x2. Well, x2 prime. Well, what happens here? That's going to be minus 2 e to the minus 2t, and then we have minus 10 e to the minus 2t. Okay, so that's just taking derivatives, and all right, same thing. 3 minus 1, 5 minus 3, x2. That's 3 minus 1, 5 minus 3 times, copy the x2 down, e to the minus 2t, 5 e to the minus 2t, which becomes 3 e to the minus 2t minus 5 e to the minus 2t, and then 5 e to the minus 2t minus 15 e to the minus 2t. Wow! Which is what? Well, 3 minus 5 makes minus 2 e to the minus 2t. 5 minus 15 is minus 10 e to the minus 2t. And, again, we compare. Aha! What do we see? We see these match. Woohoo! Nice! Booyah! Okay, so that's part A. Part A is done. All right, so let's draw a little line here. And we still have part B. Not a ton of space, but that's okay. Compute the Wronskian of the two solutions from part A. Are the solutions linearly independent? Well, how do you form the Wronskian? Well, the way you do the Wronskian is you're going to make a matrix. You're like, what? A matrix? Who would have thought? I want to make sure we can see x1, x2. And what you do is this matrix, the columns are the solutions. Okay, so we're taking the columns. We have e to the 2t, e to the 2t, and e to the minus 2t, 5e to the minus 2t. Now, we're taking this matrix, and this is a fundamental matrix. Essentially, once you start forming collections of solutions, well, technically it's not a fundamental matrix yet, but it will be. Spoiler alert. Now, the Wronskian says it's not quite this. You're going to take the determinant of this matrix. Okay, so put the solutions, these solutions are the columns, then take the determinant. All right, so 2 by 2. So down the diagonal. So we're going to have e to the 2t times 5 times e to the minus 2t. Well, what will happen? The e to the 2t and e to the minus 2t is going to become 1. So really we have 5. Subtract, go this direction. E to the 2t times e to the minus 2t, well, that's going to be just 1. So 5 minus 1, which is 4. All right, now, that is the Wronskian, 4. Now, there's a question. Are the solutions linearly independent? And what do you look at? Well, since this is not 0, these are linearly independent. So the punchline is things are linearly independent when the Wronskian is non-zero. Essentially what's really going on, and not that we need to know this for the exam, but just our intuition, saying that the determinant's non-zero says, look, you can put them together in so many different ways that every possible thing you might want to get is achievable. When the determinant is 0, it says some combinations are unachievable. And so linearly independent just says all the bases are covered. We can get everything. So the punchline, linearly independent if and only if non-zero. And now in this case, we got just a number. If we got a function of t, then we say, well, is it non-zero everywhere? Or are there cases where it could be 0? Most of the time when we're forming systems of equations, or where we have it coming from, x prime equals ax, we either have they're non-zero everywhere or 0 everywhere. So there's not sort of a fuzziness. Fuzziness doesn't come into play. All right, this brings us to number 6. Compute the matrix exponential e to the ta for the system in equation 5. Oh, okay, so let's pull back up question 5. Okay, so e to the ta, what that's referring to, this here is a. All right, so we're trying to find e to the ta. Now it says, hint, consider the solutions from part A of the problem. In other words, it's like, hey, check this out. We have solutions. Now the good news is they've done most of the work, because when we talked about finding the Wronskian, we mentioned this before. This part right here would be a fundamental matrix. So what we're forming when we form the Wronskian is we're forming a collection of solutions. And since they're linear independent, that really means that it is a fundamental matrix. All the solutions are some combinations of these columns. So this is good work for us. This we like this. And so we can just say, look, we can copy that down. And so I'm going to move my sheet around here. So I'm going to use phi. We have a fundamental matrix, phi of t is equal to e to the 2t, e to the 2t, e to the minus 2t, 5e to the minus 2t. Or in other words, we're just putting the solutions into the columns. And the solutions were given to us in part A. All right. Now, why do all of that? Well, the thing to remember is what's going on with e to the ta. E to the ta is matrix exponential, but it's like a really super cool fundamental matrix. In some sense, it's the fundamental matrix. So it's the best one. Of all the fundamental matrices that we could choose, it's the one that we want to choose. So how do we get it? Well, the good news is there's a formula for it. And if you look up on the equation sheet, and I think the equation sheet might have e to the at, but the punchline is, if you have a fundamental matrix, you take that fundamental matrix and then you multiply it by phi 0 inverse. And that gives you the fundamental matrix. We have phi of t. So let's find phi of 0. Okay, so we plug in t equals 0, we get 1, 1, 1, 5. What's phi of 0 inverse? Well, that's 1 over the determinant. 5 minus 1 is 4. That sounds very familiar from the last problem. Okay, now remember what goes on. We have to move things around. So what will happen is that we're going to switch the diagonal entries. So we're going to have 5 and 1. And then the off diagonal entries, we're going to flip the signs. Minus 1 and minus 1. Now, when in doubt, do some quick multiplication. 5 minus 1 is 4. Divide by 4, that's 1. Good. Minus 1 plus 1 is 0. That's good. 5 minus 5 is 0. That's good. And then minus 1 plus 5 is 4. Divide by 4. Yes, that's good. So when in doubt, just quickly check and see that you have what you need. So we're almost done. So what we have now, and this is our very last step, because this is also our very last problem. E to the TA or AT is equal to e to the 2t, e to the 2t, e to the minus 2t, 5 e to the minus 2t, times 1/4 5 minus 1 minus 1, 1. Now the 1/4, I always just leave that in front. So 1/4, and here we go. 5 e to the 2t minus e to the minus 2t minus e to the 2t plus e to the minus 2t. 5 e to the 2t minus 5 e to the minus 2t minus e to the 2t plus 5 e to the minus 2t. And there we go. That is our e to the at. And so once you understand what you're after, it's not too bad. Of course, you do need to know what you're looking for. But of course, that's why we practice. Practice is important. So thank you for practicing. Thank you for studying. Thank you for working hard. Keep at it. You can do this. The end is near, right? Just a little bit more, and you'll make it through. You'll pass the class. Life will be good. Life will be wonderful. All right. Thanks for coming. Hope you have a great day. Bye.